reaction that is in equilibrium, a Kc expression may be written and a Kc value may be calculated. If the reaction is a homogeneous gaseous equilibrium, then a Kp expression may be written and a Kp value may be calculated. Clearly, Kc and Kp must be related. Hi, this is Mr. B. In this video, I'll explain how the value of Kc and Kp are related in a homogeneous gaseous system. Consider the general equilibrium equation where reactant A is in equilibrium with product B. This represents an equilibrium equation in which the forward rate and the reverse rate are the same. And of course, at equilibrium, the concentrations of the reactants and products are constant. In this general equation, lowercase a and lowercase b represents the coefficients in the balanced equation. To write the Kc expression for this equilibrium reaction, divide the concentration of the products, in this case B, raised to the B power, which represents the coefficient in the balanced equation, by the concentration of the reactants, in this case A, or capital A, raised to the power of the coefficient in the balanced equation. The Kp expression for this reaction will be Kp is equal to the partial pressure of product B raised to the B power, divided by the partial pressure of reactant A raised to the A power. For a homogeneous gaseous equilibrium, both a Kc expression and a Kp expression may be written. Since both expressions may be written for the same equation, clearly there is a connection between the value of Kc and the value of Kp. Let's now examine why that is true. The Kc value and the Kp value may be related by using the ideal gas law, where PV is equal to nRT, where P represents pressure, V represents volume, N represents moles, R, the universal gas constant, 0.0821, and the Kelvin temperature. This equation may be rearranged to solve for P by dividing through by V. So the partial pressure of each gas in this equilibrium will be P is equal to nRT over V. Now applying the ideal gas law to both the products and reactants will generate the following relationships, where the partial pressure of A is equal to moles of A, RT over V, and the partial pressure of B will be moles of B times RT divided by V. Now inserting this information into the Kp expression will yield the following, where Kp is equal to moles of B, RT over V, raised to the B power, divided by moles of A, RT divided by V, raised to the A power. Since each expression contains RT, the RT may be factored out. This will yield moles of B divided by volume raised to the B power divided by moles of A divided by V raised to the A power times the factored RT, B minus A. For dividing exponents, subtract the exponent in the denominator from the exponent in the numerator. This will yield RT raised to the B minus A power. Since moles divided by volume is actually the calculation for molarity, we may rewrite it as follows, where moles divided by volume is equal to the concentration of B raised to the B power. And for reactant A, moles divided by volume is actually the concentration of A, which is raised to the A power. And of course then multiplying by RT raised to the b minus a power. The expression may now be simplified, where Kp is actually equal to Kc RT raised to the delta n, where delta n represents the change in moles, b minus a. And of course, in this expression, to solve for Kc, simply divide Kp by RT delta n, or change in moles. If there is no change in moles, or delta n is equal to 0, then Kc is equal to Kp, since any value raised to the 0 power is 1. As an example of how Kp and Kc are related, consider the following. In this equilibrium equation, reactant dinitrogen tetroxide is in equilibrium with nitrogen dioxide. And of course, the balanced equation will be 1 to 2. Suppose we're given a Kc value of 4.63 times 10 to the minus 3, where both Kc and Kp are dimensionless values, and the temperature is given at 25 degrees Celsius. What is the Kp for this equilibrium? The Kc expression for this reaction would be written as follows, where Kc is equal to the concentration of the products, in this case, nitrogen dioxide raised to the second power, which reflects the coefficient in the balanced equation, divided by the concentration of dinitrogen tetroxide. The Kp expression would be Kp is equal to the partial pressure of the product, the nitrogen dioxide, raised to the second power, divided by the partial pressure of dinitrogen tetroxide. Kp is equal to Kc times the ideal gas constant, 0.0821, times the Kelvin temperature, in this case 298 K, raised to the change in moles power, where the change in moles would be 2 minus 1, which reflects the coefficients in the balanced equation. So the Kp value for this homogeneous gaseous equilibrium will be 0.113. Now suppose you're asked to calculate the Kc value given a Kp value. Consider the following equilibrium equation, where water is in equilibrium with its elements, where 2 moles of water is in equilibrium with 2 moles of hydrogen gas and 1 mole of oxygen gas, where the Kp value for the equilibrium reaction will be 2.0 times 10 to the negative 42 at 25 degrees Celsius. Now substituting the data, we yield the following Kc value, where Kp is 2.0 times 10 to the negative 42, divided by R, 0.0821, times the Kelvin temperature, which is 298 K, raised to the first power, which represents the change in moles. And the Kc value will be 8.0 times 10 to the negative 44, where of course the Kc value is dimensionless.